So, welcome to the laws of set algebra. Now I've written them up there, and actually only half of them, we'll get to that. But the reason that I've written them up and that we look at these laws, these so-called laws, is that if you remember when we're trying to prove little facts about sets, well, you wouldn't want to go to that level of basic knowledge when you're talking about more important mathematics. So it's a good idea to prove a whole lot of basic things first and use them as bricks, as the foundation for a big house of knowledge, mathematical knowledge. So here are some of these bricks that we could prove. In fact, we should prove all of them, but we're not going to. So here we have the commutative law, the associative law, and so forth, and I'll go through them in turn. But the basic view here is that we have a lot of very useful bricks of knowledge that we can then henceforth, after this, consider to be proven, and then we can use them to make even higher order bricks, so to speak, and slowly build up our building, our edifice, our monument of knowledge. Now, looking at all of these, some of them are very simple, but they're also quite fundamental. So the first one here is the commutative law. If you have A and B, then they commute in the sense that we can swap them around, or they can travel past each other. They can swap. They can together mutate into each other's shape, so to speak, swapped form, in other words. So A intersect B is also B intersect A, and of course, if you want to show a little diagram of it, you could draw a tiny little picture where we have A and B and C. Yep, oh, it's so tiny that not even I can read it at that distance, and you probably can't see it at all, but you can show just drawing little pictures, little Venn diagrams, and of course that must be true. And that might convince you that this is a valid result, and we could call it a law if we wanted to then, as we do here. And if you wanted to be more rigorous and convince everybody, then you maybe should write it up as a formal proof. In the case of just your own satisfaction, I think it's actually a good idea just to draw little pictures in case you ever get to doubt any of these laws, or if you can't quite remember a law and how it was, well, draw a little picture and we'll have a mental image of what's going on. The names of the laws here, and we've got quite a few of them. Some of them sort of make sense, especially since some of the terms like commutative, that expression you find in a lot of mathematics, so you'll get used to it if you're not already. Same with associative and distributive, idempotent. The others you'll sort of just have to memorize, and that's a bit annoying. Hopefully you're better at memorizing things than I am. Now, before we go on and look at each of the laws in particular, I should say that this is only half the list. So for every one of these laws here, there's another law. That's the dual law of it. So for instance here, I could have written also A union B is equal to B union A. So what I'm doing here is that I'm swapping the intersection with a union. And in fact, I can do that. So this gives me a new law. And in fact, I can do that everywhere here. Wherever you see an intersection, swap it with a union. Wherever you find a union, swap it with an intersection. So then we get some laws here. A union B union C is equal to the right-hand side, which I have unfortunately written a little bit too closely here, and so forth. And you can do that the way through, and you get a new set of laws for each, or a new law for each of these laws here. There's one detail that we have to make sure of to get that to work, and that's that the universal set, which I have here, is swapped with the empty set, and the empty set with the universal set. So you swap unions and intersections, and you also swap universal sets with empty sets. If you do this, then you go from one set of laws to the other. By the way, at one point or another, it might become a little bit difficult to see whether we're talking about unions or the letter U. So if you do worry about whether you can read that as a union or a union symbol or as the letter U for the universal set, you could just make it a little bit more U-like, so then you can see the difference. Okay, so you could prove all of these, and you probably should. It's good practice that you do this, but many of them you can just draw a little picture. For instance, this one here, the double complement law. Again, here we have A, and if we're looking at the complement, A, so if A is in there, and the complement is there, then the complement of the complement is A again. It's all intuitively clear, well, most of these things, but again, it's not a bad idea to prove it. So let's go through them all just very quickly. So the commutative law says that it doesn't matter which order we write A and B in. If we're using intersection or unions, we get the same result. The associative law says that if you're only dealing with intersections or only dealing with unions, then we can put the brackets where we want, which is a great thing. That corresponds to saying, well, if we're only dealing with addition, like 1 plus 2 plus 5, then it doesn't matter if we put the brackets there or the brackets there, we'll get the same result. So we don't have to care about brackets, and in fact, we could leave the brackets out. If we're only dealing with one operation there, there's no ambiguity. And the same thing, 1 times 2 times 5. It doesn't matter where you put the brackets there, like here or there, you'll get the same result as well. So in this case we get 8, in this case we get 10. So in the same case here, for the associative law says that we don't need brackets if we're only dealing with one operation, here the intersection or here the union. On the other hand, if we are dealing with a mixture of operations, then we need to be very careful about our bracketing. We need brackets, as we've seen in an exercise before, or 2 exercises in fact, and that is what the distributive law can help us with. So if you have A and you're intersecting into a bracket, just like multiplying into a bracket, then you have that A intersect this bracket, well that's A intersect B, union A intersect C. And of course there's the dual law that says the opposite, or the dual where you're swapping the union and intersections around. In terms of numbers, you could think of it like this, like 5 times 3 plus 7, that's equal to 5 times 3 plus 5 times 7. So that's the sort of thinking if you do want to have something to think about and try to remember that law. The next one there is the absorption law, and that's slightly different. It says that if you take the intersection with the union of A with some other set B, you're back to A. And that sort of makes sense if you think about it, but it is out of all these laws, this is one of the slightly more exotic ones. So if you start with A and you add something by taking the union with B, but then you restrict it back to A by taking the intersection with A, then you're back to where you started. So it's quite simple, but it's possibly hard to remember. So you have an intersection there and a union there. If you flip those upside down, both of them, then you also have that this is true. That's the absorption law. Now the identity law says that if you take A and the intersection with everything, the universe, well the universal set, then you just get A itself, which is obvious. The dual of this is that if you take A and the union of the empty set, because now we're swapping the intersection with the union and the universal set for the empty set, well that leads you back to A. We're adding nothing. And of course, this is also equal to what you get if you swap those two around by the commutative law. The next one is the idempotent law. It says that the intersection with any set with itself is the set itself. That makes sense. We've already seen the double complement law. The domination law says the opposite of the identity law, or not quite the opposite, but it has the opposite statement, that A intersected with nothing is nothing. A intersected with the empty set is nothing. So what's both in A and the empty set? Well, nothing. And again, there's a dual form where it says A union the universal set. That's everything. So you take everything and you add A, which is already in everything, that gives you everything. That's the domination law or the universal bound law. Both of those are called the same. What do we have next? We have the intersection with complement. So here we have A intersects its complement, that's the empty set. Now we also have the dual law, which is now called something different. All of these laws, the commutative law, actually is the name for two laws. The associative laws, there are two laws with that name and so forth. When we get to this one, intersection with complement, there we have a different situation. We have intersection or union with complement. These are the two dual pairs here. Here we have that A union, its complement, is the opposite of the empty set. It's the universal set. So you take A and everything not in A, then you get everything. So that's quite simple. The last one here is De Morgan's law. Now that's a slightly special law because it's a bit more clever than the other ones, and it's also very, very useful. And it was, in fact, invented by a person, De Morgan, who has now this name for himself. De Morgan, he's a roughly 200 years ago British citizen born in India by British parents, came to Britain, and he led a moderately interesting life. Read up about him if you want. But he contributed a lot of good mathematics, including this statement here. And of course it's dual, which is that if you take A intersect B and take the complement of that, then we get that it's A complement, B complement, and now we swap the thing in the middle, which was an intersection, and now it's a union, and that's also called De Morgan's law, even though we strictly speaking have two different laws there. So these are the laws of set algebra, and now you could prove any of them if you want, but let's assume that we have done that. Please do it just as proof practice, but let's assume that we have done that now. And now we'll take all of these for granted and let's use them. The only caveat there, the only thing that we need to do in order to use them is, if you want to be presenting things nicely, for instance in a proof or an explanation or wherever in a calculation, is to refer to the law that you're using so that everyone knows what exactly you're doing. So let's do that. Now that we have the laws of set algebra, our building blocks for bigger edifice of mathematical knowledge, we can actually use those building blocks as tools in themselves. And I'll show you one way that we can do that. Here we have some mathematical expression of sets A's and B's that are somehow operated on by intersections, unions and complements, and it looks a bit messy. We might wonder whether it's indeed possible to simplify this expression. So that's what we're going to do using those laws of set algebra. So the very first thing that you might look at is that complement of this bracket here. It's a complement of something intersects something else. So immediately you should think, De Morgan's law. So let's use De Morgan's law here. So we're taking De Morgan's law and applying it to this bracket. So before I do more, I'll just write De Morgan's law. De Morgan's law. That's supposed to say De Morgan's law, if you can read and guess a little bit. That's very messy, but as long as you write what you're using, then it's okay. You must specify what law you're using if you get a test or exam that involves such a problem. So let's see, how do we use De Morgan's law here? Well, we look at what we're intersecting here. We've got A complement and B, and we take the complements of those, so A complement and B complement, and then we take the operation that's there and flip it upside down. So now it's an upside down bowl, we flip it up, it's a right side up bowl. Now it's the union instead of the intersection. So the next thing that we see here is that we have a double complement. So let's hurry and use that double complement law. So we get A instead of A complement, and then B complement. So this is the double complement law. Now if we look at this expression here, we have something, something, something and some brackets, but we have only the union operation going on. So in that case, we can use the associative law that says that it doesn't matter where we put the bracket. So let's put the bracket elsewhere, like A union B, complement B, and the union there, and move the bracket over there using the associative law. Haha, now look at that. We have B and B complement union together. So that gives us the universal set, and great. One little technicality, and you could argue whether this is being a bit too pedantic, but if you did want B to come first and then B complement, as it's sometimes expressed in the union with complement law, then you might first want to say A union B complement by the commutative law that says that we can swap these two around, and that way we get an expression that we're comfortable. It might not have any sort of lingering doubts whether the expression of this next law that we're going to use is applicable. So here we have A union, and the law that I'm talking about is the union with a complement law. So union with complement law, which says that B and its complement, the union of them, is just the universal set. And then we're pretty much done, because then we've got that A union the universal set is the universal set. So that's the domination law, and there we're done. So domination law, and you can't simplify any better than that. It's just one symbol and we're done. So all of that was in fact just a complicated way of writing the universal law, and we were able to simplify that complicated expression down to this very simple expression just by using the laws of set algebra in a relatively straightforward way. But do remember to signify which laws you write along the way. So here's an exercise. Use the laws of set algebra to simplify this messy looking expression. And this is a very typical sort of question that you might meet in tests or exams. So please pause the video, try to work it out yourself, and do so now. Okay, so let's do this. So we've got this set here, and I'll write it up again because now I'm going to present the solution. So it's bad form if I just keep writing there, which would save space, but unfortunately bad form. Okay, and the hardest thing about these sort of problems is to accurately write them up. So let's just see whether we've got everything the same there and there. We do. So now the first thing that you would generally try to check were to see whether there were any brackets containing some unions, or here intersections where there's a complement outside of the bracket, because then we can use De Morgan's law on it. So let's do that. In fact, here we do have two sets that are intersected with a complement outside. So if we apply De Morgan's law here, we get that the complement there disappears, and instead we have complements to the sets there, A complement, B complement, and the intersection gets flipped upside down, so we have a union there instead. And this is by De Morgan's law. Remember to write which laws you're using, those in particular. So now we have that law there. Now we've got A intersects a union of sets, and then we have something else there. We could possibly use this distributively on these two sets, or we could look at A multiplied into the set, so to speak, or intersected, so to speak, using the distributive law. So there are several approaches to simplifying these. Here we'll choose to say A intersect A complement, I might dust that. I might. Yeah. So here we have A intersect a union of things, so we might take the distributive law, which multiplies into the brackets, so to speak, intersects into the brackets. A intersect the first term, which is A complement, and then we take the union of A intersect again, the next term, which was B complement. And then we have this outside term, which we haven't bothered to look at yet. So this is the distributive law that we're using. Distributive law. There we go. And now we see, haha, we have A intersected with its complement. So we can immediately go use the intersection with complement law to say, well, what's in A that's also in A complement? Nothing, that's the empty set. And then we have the rest here. We write it again. Union B complement. So this is intersection with complement law. Intersection with complement law. Here I'm trying to write small in order to get it to fit. Okay, now here we have the empty set unioned some other set. That's just that other set. That's by the identity law. So this all collapses down to this expression here. And we can see that first we expanded the expression and it got worse and worse, not simpler as we were trying to do, but eventually we are getting something simpler when everything falls and steadies at the end. So here we've got that expression, and that was by saying the union of the empty set and some set, which is addressed by the identity law. That's sort of the opposite as the domination law. Okay, now we have A intersect B complement, union B complement. Aha! So here we've got an intersection of B complement, and then outside the brackets we have a union of B complement. So that leads us to say, okay, we're mixing intersections, and we have this outside set being inside the set, inside the brackets as well. So that's probably the absorption law that we can use there. And if you quickly sort of mentally think, does that make sense? Then you could say, okay, I start with the B complement there. I restrict it down to A, so I'm cutting some of B complement away, but then I'm adding it again with that union, so I'm back to B complement. Okay, yeah, that all is equal to B complement by your quick thinking there. And if you want to give the law that actually, allows us to do it without the thinking, that's the absorption law. And we are done, because B complement. I can't figure out any way of writing that more simply, and I doubt that you can.